All right, so this is the first lesson of Unit 4. Unit 4 is going to be all about t-testing. We're actually going to do something called a confidence interval today, but Unit 4, generally speaking, is t-testing. The last slide, I will do an example. You should always write down the example, but make sure you write this one down word for word, because the calculation to this is basically identical every time we do it. Okay. So what is the purpose of t-testing? So we just finished up in Unit 3 the z-test. But in order for the z-test and to do z-score math, we must already know the population mean and population standard error. So z-score is only helpful if you already know the population mean and the population standard deviation. The difference of z-test and t-test is unbelievably important if you take AP statistics, because you got to pass the AP test. For on-ramps, they're on different tests. So it's not that it doesn't matter, but they're never going to be on the same test together. So just kind of remember what we've been talking about. But a t-test is used if we do not know the population information. So today we're going to do something called confidence intervals. So confidence intervals are used you take a sample of data and use that information to estimate the mean of the population. So let's say I want to know the average SAT score of a high school senior. The population would be I need to survey every single high school senior in the United States of America, so millions of people, and find their SAT score and find the average. Well, I'm not going to do that. Let's be real. So I'm going to sample, let's say, 100 or 1,000 or something. High school seniors. I'm going to find their average, and I'm going to use their average to estimate the true mean of the population, right? It's very similar to the sampling distribution, what we did in Unit 3. But this is more mathematical and less theoretical than the central limit theorem that we have just discussed in the previous chapter. The math of a confidence interval is X bar plus or minus error. So again, anytime we use a sample of information instead of the entire population, there is some error involved. We are educated guessing here. Okay, so there's a way to calculate the error. It's over here on the right. I can show you. I don't know if y'all can see me twirling my mouse around or not. So the confidence interval is X bar plus or minus the error. So X bar is my sample mean. So again, we're going to find the mean of a sample, and then we're going to add and subtract the error off of that. The error, we quantify the error with the formula T critical, which I will discuss in a second. But the critical value of T comes from the T table, which again, I will discuss in a second. And then we multiply that by standard error. Hopefully the standard error formula looks familiar because it is the exact same formula from when we did the Z table. But standard error is standard deviation divided by the square root of sample size. And really that could be S because it's going to be the standard deviation of my sample, but whatever. It's just notation. So we have the standard error formula. But instead of just using standard error like we did in Chapter 3, we're going to take standard error and multiply it by the critical value of T, which again, I will talk about in a second. Degrees of freedom is only necessary to find the critical value of T. So these two will make a lot more sense in 30 seconds or so. But degrees of freedom, when they discuss that, is the sample size minus 1. Okay, so if it's n of 27, you subtract 1, so you'd have 26 degrees of freedom. Again, that is only used to read the chart, so let me get to the chart. So what we were actually doing today is something called a confidence interval. Again, these are used to estimate the true, quote unquote true, I want you to focus on the word true, population mean without surveying the entire population. So again, we can estimate the mean of a very, very large population, and this guess is going to be almost always true. In fact, the standard confidence interval is 95%. So if we survey the entire population, we are 100% confident that our answer is correct because we surveyed the whole population. Nobody does that. So you survey a sample, we use a 95% confidence interval, and we are 95% confident that our answer is correct. And in stats, we're okay with being 95% we are okay with being correct 95% of the time. That's good enough. Okay. So 95% of the samples, this percentage can technically change, but 95 is the common one, we take should contain the true population mean. So if we take the sample mean and make a confidence interval, and we do that 100 times, 95 of those samples would contain the actual mean. Okay. So again, if you were constructing a 95% confidence interval, you were saying that you are 95% confident that the true population mean falls between blank and blank. I'm hoping that all of this makes more sense when I do the example, but I want these words in your notes, word for word, because quiz 4 is open note. So if you have this stuff written down, it will hopefully jog your memory and help you with conceptual questions on the quiz. Okay, so please write this down word for word, even if you need to pause the YouTube right here. All right, now let's talk about T-critical for a second. So T-critical is a chart. If you were sitting in my classroom right now, it is the pink laminated sheet of paper in the back and those black shelf things, so you can go grab it. It's probably already on your desk by now. But the T chart is the pink sheet. We're done with the green sheet until the final exam in May. So we're on the pink sheet. So what we do with the pink sheet of paper is we look at the intersection of the degrees of freedom and the confidence interval. So remember that the first one says 100 degrees of freedom and 90% confident. So 100 degrees of freedom and 90% confident. So you have your confidence intervals up here. Okay, then you have your degrees of freedom, down here on the far left. So 100 degrees of freedom is this row, right? So you have 100 degrees of freedom. It told me we were 90% confident, so go up here. Ignore the one-tail, two-tail stuff. This is baby stats, so we don't care about the difference. So 90%, 100 degrees of freedom, my answer is 1660. Is that my... Uh-oh. There it is. So my answer is 1.660. I'll explain plus and minus again with the example. So the second one says degrees of freedom equals 6 with 95% confidence interval. So we go to 6 degrees of freedom. We are 95% confident. So my answer is 2.447. Okay, that is the only purpose of degrees of freedom, but it helps us read the T-critical chart, okay? And we'll need that T-critical to find the margin of error. Okay, I know I've rambled for 8 minutes, but stay with me. Here's the money slide, okay? These are the questions you're going to be asked. There's a 1,000% chance you are asked to construct a confidence interval on the quiz. The question will be structured exactly like this with different numbers, so we need to know this example, and this example needs to be in our notes verbatim, okay? All right, here we go. So a researcher wanted to know if the amount of water in a water bottle was truly 16.9 fluid ounces. If you got a water on your desk, just look. That's what it should be if it's a normal bottle. It's a smart water, so I think it's probably bigger than that. The student collected a sample of 61 water bottles and measured the water in each bottle. Okay, measured each amount. The average amount in our sample was 15 fluid ounces with a standard deviation of 1.2. Okay, so we work for Nestle or Ozarka or whatever water you drink. And we're trying to figure out, does our water actually have 16.9 fluid ounces? Because I don't want a bunch of people suing me. Okay, so it's our job to figure out if our bottles have the correct volume that they are supposed to. Okay, so let's see how this works. So first, we're going to calculate our margin of error, okay? To calculate margin of error, you need to first calculate standard error, which again is the same from chapter 3, but standard error is standard deviation divided by the square root of sample size. So the standard deviation is 1.2. I had 61 water bottles, so we put the numbers where they go. And I get a standard error of 0.154. Okay. We talked about in our second slide or first slide, whatever, where the formulas were, that it's not just standard error anymore. It's margin of error. And margin of error is standard error, which we just calculated to be 0.154, and we multiply standard error by T critical. Okay? Now we got to remember T critical. T critical was from the last slide. It is the pink sheet of paper if you're sitting in my room. Okay? If you're at home, just pause the YouTube video when I stop on the T critical chart. Don't Google it. Make sure you're using the UT one because they all can be slightly different. So the T critical is we are 95% confident and we have 61 water bottles. If we have 61 water bottles, remember degrees of freedom is n minus 1. So if we have 61 water bottles, we have 60 degrees of freedom. So 60 degrees of freedom. And we are 95% confident. So my T critical happens to be a very nice number, but it's 2.000. Okay. Side note, real quick. Let's say you get like 90 degrees of freedom or something. You are always ultra conservative and go down to the lower number. So if you ever have a degrees of freedom between these numbers at the bottom, go to the lower number. But we found the T critical to be 2.000 from the chart. We multiply that by standard error, which we found over here in yellow to be 0.154. So we have a margin of error of 0.308. Okay, so with a confidence interval, we can actually quantify the amount of error we have in this study. Okay. So the confidence interval, I ran out of room, so I couldn't write margin of error again. That's why I wrote MOE. But MOE is margin of error. So the confidence interval is the sample mean plus and minus the margin of error. Okay. So the lower bound, or the smaller number, is the sample mean, which was 15, minus the margin of error. So it's this. The upper bound, or bigger number, is 15 plus the margin of error. Okay. So we have the lower bound, which is 14 and change, the upper bound, which is 15 and change. So my sample mean was 15, but we're not going back to our boss at our water bottle company and telling him, hey, dude, the answer is 15 because I grabbed 60 water bottles. Okay. We're going to go back to our boss, and this is the sentence that we're going to say. So the sentence we're about to write, this is the mathematically correct sentence that needs to be in your notes. Will that go away? What is wrong with this? That needs to be in your notes. And we need to basically memorize this for the exam, but for the quiz, if you write it, the structure of the sentence should always be structured something like this. Okay, I know I said structured too many times, but sorry. The conclusion is we are 95% confident that the true, and again, focus on the word true, population average is between 14.692 and 15.308. Okay? So the statement is we are making a 95% confidence interval, so we are 95% confident that the actual or true population average is between 14.692 and 15.308 because that's what our math told us. Okay? There's two different questions they're going to ask you with this. One, construct the interval and write this sentence. Okay, so we did our math. We wrote our conclusion down there. The second is going to say, so is your machine functioning properly, or is your company doing what they're supposed to do? So remember, in the question, it told me that the average water bottle should have 16.9 fluid ounces. Okay, should have 16.9. I just told you that I'm 95% confident that it's between 14.7 and 15.3. So if I'm telling you water has 14.7 to 15.3, it does not have 16.9 fluid ounces, so your machine is broken, your bottle is too small, something is wrong because there is not the correct amount of water in your bottle. Okay? But a confidence interval, recap one last time, then I'll be quiet because I don't want this to be too long. But you calculate your standard error, which is the same as last chapter, which is standard deviation divided by the square root of sample size. You take the standard error of 154 and multiply it by the critical value of t, which is 2.000. We found 2.0 by going to 60 degrees of freedom, because that's one less than sample size, and 95% confident, and they intersected at 2. We multiplied that by standard error to get my margin of error of 0.308. We took this margin of error and we added and subtracted it from the sample mean, or X bar. And then the lower bound and upper bound is just put the smaller number first, because you need to do addition and subtraction. The smaller one is the lower bound because it's the smaller number, and the bigger one is the upper bound because it's the bigger number. Okay? And then the conclusion is, once you have lower bound and upper bound, that you were 95% confident that the true population average of blank, which in this case is fluid ounces, is between blank and blank, which is 14.692 and 15.308. All right. Again, make sure this is in your notes word for word. And then y'all can always ask me questions about this in class.